Hello everyone, welcome to YourPedia Education. So as you know, ISRO released the notification and the form filling is already going on. So that is related to the scientific post, right? So today we are going to discuss some important questions that are related to that ISRO exam, and these are from the analog electronics subject, right? If you want to prepare for that exam, YourPedia is already providing the online classes for that one. You can join the YourPedia to prepare the ISRO classes, right? And lots of students are currently going through these classes, right? Okay, let's start. The first question is, for the circuit shown in below, the cut-in voltage of heat diode is 0.7 volt. What is the value of V and I? So from this circuit we have to find this I value and this V value. So what we are seeing here, there are two voltages. This is 1 volt, this is 3 volt. So what happens? First, this 3 volt diode will try to be on, because this is 1 volt, it is taking too much time to on. So first this diode, let us take this is D2 and this is D1. So your D2 diode will on, D2 will on, and as your D2 is on, the voltage at this position is become how much? This is take a drop of what? 0.7 volt. It means the voltage at this position is 3 minus 0.7 is equals to 2.3 volt. So what is happening at this position? The voltage is 2.3 volt and this voltage is greater than 12 volt. So it means this diode, when the diode D2 is on, it will prevent to diode D1 to be on, right? So only diode D2 will on and the circuit is become like this. The D1 is off, right? Understood? So D1 is off in this circuit and D2 is on, right? So when D1 is off, D2 is on, the circuit now become like this.
Yes.
Right. So this will be your output voltage. When you apply the KVL from here to here, that will be 3 minus 0.7 is equals to V out. So the V out voltage is 2.3 volt. Now we have to calculate the current through this resistance, that will be I. This is a 2 kilo ohm, not 500, 2 kilo ohm resistance. So when it is a 2 kilo ohm resistance, what we can say, this is 2.3 here. So the voltage across this resistance is 2.3 minus 3 divided by, this is the voltage across this resistance and the resistance is 2 kilo ohm. That will be the current I. So current I is going to be 5.3 divided by 2. That is 2.65 milliampere. Answer will be A. 2.3 volt, 2.65 milliampere. So whenever you are going for ISRO exam, ISRO exam, don't be think like that the exam mostly theoretical, that exam is conceptual, and you can say the calculative part is more in that ISRO exam. Yeah, basically last year exam is bit easier from the past exam of ISRO, but in the past exams what we observe that they are asking the calculative questions, right, like this, right? Next question. The circuit shown in the figure below, the value of ID and VD are, we have to calculate the ID value and this VD value. So what we can do, whenever you see this type of questions, what you can do, first you have to assume that your diode, this diode will be off. We have to assume that thing, and we are trying to find the voltage at this terminal V1 and we are trying to find the voltage at this terminal V2, right? We are calculating the voltage V1 and V2. When we calculate this V1 and V2 voltages, we can easily find that this diode will be on or off, right? Okay, so what we assume that the diode is off, and when your diode is off, it will behave like a open circuit. Now what is happening here, this is a resistance, this is a resistance, and another one, this is a resistance, this is our another resistance, this is ground, this is ground. Let us take the voltage here is V1 and the voltage here is V2. This is 8 volt and this one is 4 volt. plus 4 volt. Now use the voltage division rule. We can calculate the voltage across 10 kilo ohm, 10 kilo ohm. When two resistance are equal, the voltage will divided into two parts. Means if here is 8 volt, then 4 volt will come across this 10 ohm, 4 volt come across this 10 volt. So the V1 voltage is 4 volt, right? Again for the second part, this is 10 kilo ohm, this is also 10 kilo ohm. Now we calculated the voltage across V2. V2 is the voltage across this 10 kilo ohm resistance. Again, these two resistance are same, it means the voltage across this 10 kilo ohm resistance is half of this voltage, that will be 2 volt, right? Because the resistances are equal. So what we are saying, this is the positive terminal of the diode Vp and this is the negative terminal of the diode Vn. So if anything is not given in the question, then what we can do, we can assume that diode is ideal and to on this diode Vp should be greater than Vn. But what we are seeing here, that Vp is 2 volt and Vn is 4 volt, which is less than 4 volt. It means what is happening, this diode will be off, and when your diode will be off, the voltage across this diode, current through this diode will be 0 ampere. So there are two options which shows that the current is 0, and we are calculating the Vd. The Vd is what? The Vd, voltage across this diode, this positive terminal is here, negative terminal is here. We can say the V2 voltage first, V2 minus V1, that is V2 is how much? That is 2 minus 4, it going to be minus 2 volt. So answer will be C, 0 volt and minus 2 volt, like this. Next question. The cut-in voltage of each diode shown in the figure is 0.6 volt. Cut-in voltage is 0.6 volt. Each diode has current of 0.5 milliampere. So basically current is flowing through this, that is 0.5 milliampere. This is current is going to be here, that is 0.5 milliampere, right? So basically we have to calculate the value of this R1, R2 and R3. This is also 0.5 milliampere, right? So basically when 0.5 is coming here, 0.5 is coming here, that will be 1 milliampere here, right? Next 1 is coming down, 0.5 coming here, that will be 1.5 milliampere, right? Okay, this is 10, the drop of this diode is 0.6 and this is 5, drop of this diode is 0.6. So if I calculate the voltage here, the voltage at this terminal is 4.4 volt, correct? 4.4 volt. Next, if I calculate the voltage at this terminal, this is 0 minus 0.7, that is become minus 0.7 volt. Next is 5 here. Now we can easily calculate this one. The voltage at this terminal is what? 10 minus 0.6, that is 9.4. So again apply the KVL. So the R1 resistance is going to be voltage drop across that resistance 9.4 minus 4.4 divided by the current 0.5. So that will be 5 divided by 0.5, 10 kilo ohm. The first resistance is 10 kilo ohm. You can check it, only one option that is having 10 kilo ohm, A option. Now you can similarly calculate the R2 resistance. The R2 resistance, see basically in every exam like ISRO where the calculator is not allowed, then they will put the options like that. You can calculate only one value and you will get the final answer. That will be 4.4 minus 0.7 divided by 1, around 1 kilo ohm. So that will be the A is the answer. Like that you can calculate the last value. Okay, next. Oh, that is not 0.7, that is 0.6 volt, right? So that's why it is going to be 5. Yes, similarly you can calculate the last resistance. Next question. Yeah, the circuit shown in the figure, right? What is the current through the Zener diode? We have to calculate the current through this Zener diode. So basically what we can do here, this is the circuit, right? We can replace this Zener diode by, because this is 10 volt here, so 10 volt. First what we have to do, whenever you see this type of circuit, just remove this Zener diode. think like that, that this Zener diode is in off state, it is not in the breakdown, right? So first what we can do, we can calculate the voltage across this resistance. That will be how much? It is given to you 3.5 volt, right? It means if it is 3.5 volt, yeah, it's easy now. It is 3.5 volt, it means that is greater than 3.3 volt. It means this diode is on. Okay, if 3.5 volt is here, the same voltage will applied here, 3.5 volt, right? 3.5 volt is here, 3.3 volt is going across this diode. Then how much voltage will left with this RZ? The voltage across RZ is going to be 0.2 volt, means 3.5 minus 3.3, 0.2 volt divided by 0.1, it means what will be the value? Oh sorry, 2 ampere. The current is 2 in milliampere, right? Because it is in kilo ohm. Sorry, that will be 2 milliampere, right? So what we did, this is 3.5, this is the Zener diode voltage is 3.3. It means this Zener diode take 3.3 voltage across the Zener diode. Then how much voltage remaining across this RZ? That is 0.2. Then 0.2 divided by this resistance 0.1 kilo ohm, which will give you the current. That is 0.2 divided by 0.1, that is going to be 2 milliamp. Yeah, next question. Assuming that diodes are ideal, right, the current through D1, we have to calculate the current through this one, I. So what you are seeing here, we have to calculate the I. Okay, let us first assume that D1 is off, right? D2 is forward bias, because D2 is connected to the minus 8 volt, the N terminal is connected to minus 8 volt and positive terminal is connected to 5 volt. So first you have to assume that which one has the most probability to be on, you have to put that on. So we assume that this D2 is off, D1 is off, D2 is on. Now the complete circuit is become look like this one. This diode is on 8 volt and this will be 5 volt. This is 8 volt here. Now we are trying to find the voltage at this terminal. Let us take that is V2, or let us take V1, any value, right? We are trying to find this V1 voltage. So that V1 voltage, by using the nodal, V1 minus 5 by 1 plus V1 plus 8 by 1 equals to 0. From this one, twice of V1 is equals to 3, minus 3, right? Because this is 5, this is 8 minus 3, so V1 is going to be minus 1.5 volt. So if the voltage here minus 1.5 volt, so this diode D1 can never going to be on, because it is required a voltage which is greater than 0 to be on. So what we are saying, that D1 diode will be off, and if it will be off, it will replace by the open circuit, and current through this one, that will be 0 milliampere. So answer is what? 0 milliampere. Yeah, the common emitter current gain of a transistor beta is given to you, VB on 0.7. What will be the value of VBC? VBC, this is the base terminal, this is the collector terminal, this will be the emitter terminal, right? So we have to calculate the voltage VBC. The first, we are using the KVL, apply the KVL at this loop, and we are calculating the IB. That will be 8, right, 8 minus 10 times IE minus 0.7 minus 10 times IB is equals to minus 2 volt. And when you solve, the IE value is beta plus 1 times IB. When you solve that for the IB, you will go to the IB is 12.08 microampere, right? From this IB you can calculate the voltage at this VB terminal, right? The VB terminal voltage, yeah, you can calculate the IC and IE. From this IC and IE you can calculate the VCE, right? VCE, how we can calculate the VCE? Collector to emitter voltage, apply the KVL in this loop, right? So when you apply the KVL, 8 minus 10 times IE minus VEC minus 3 times IC is equals to minus 8. Put IC and IE value, you will go to the VC value, right? When you go to the VC value, you can calculate this value VCB. So we can write that VEC is equals to what? VEB minus VBC. So you can put these values. This is 0.7 volt, and you calculate this value, you will go to the VBEC. Okay, he is asking VCE, not VBC. Oh, that is printing mistake. VEC, he is asking for VEC, not VBC, VEC. So VEC, emitter to collector, you can directly calculating by applying the KVL in the output loop by putting this value, that VEC is going to be 4.1 volt. Next. The common emitter current gain of a transistor, beta gain, VB1 is 0.7, the value of VC. This time we have to calculate the VC. Again, to calculate the VC, you have to apply the KVL in this loop like this. So that will be 5. Again, remember, IC current is going inside this transistor and IB current is going here. So basically the current here is, that is IE, the same current is here, that is IE. So when you apply the KVL, that will be 5 minus 10 times IE minus 20 times IB minus 0.7 minus 2 times IE equals to 0, right? So we can say the 5 minus 0.7, if you calculate the IB, right? I am calculating the IB here. That is going to be divided by 10 times 10, okay, 10 plus 2, 12. 12 times beta plus 1, 76 plus 20, right? That will be your IB. IB is going to get, you are getting 4.62, and IC is beta times IB, and VC. Now you can calculate the VC. VC is easily calculated, that is 5 minus how much? 10 times IE, right? We got the IE from this equation, right? Equals to what? VC. So directly put the value of IE, you will go to the IB, beta 1 plus RC. Yeah, you got 1.49. Yes. Below transistor beta is given to you. Again VC, because we are not practicing on this PNP transistor, we are mostly do the question on NPN transistor. So today I bring some questions which are from PNP transistor, right? Okay. In this case, what is given? IE is given to you, beta is given to you. You can calculate the IB. We have to calculate VCE, VEC, emitter to collector voltage, this voltage. Yeah. So to do that, we know that VEB, right? VEB, emitter to base voltage, that is 0.7 volt. Then VBC, base to collector voltage, we have to calculate this, and then we have to calculate the VCE, right? So basically first I calculate the IC, because this is IE is given to you. You can calculate the IC. IC is going to be 0.7. Then we calculate the VC. VC voltage is this one, and then calculate the VE voltage, emitter voltage. Right? How we can calculate the emitter voltage? You can do one thing. You can apply the KVL from this point to the ground like this. From here, this is VE. Right? We apply the KVL from here to here. We calculate the VE voltage. Then this VEC can be written as VE minus VC. Yeah, we know that VE voltage and VC voltage, you can subtract them, you will got the 6.09474. Again the same question, the circuit shown below. These are the very good questions if you observe here. The Zener diode voltage is VZ equals to 5 volt, beta is equals to 100. We have to calculate ICQ and VCQ. See, basically if I connected here 12 volt, so it means this Zener diode in breakdown region, so it will be replaced by a battery of how much? 5 volt, like this. So there is a voltage, this is 0.7 here, 5 here, like this, 0.7 is like this. So what we can say, the voltage at this terminal is 5.3, right? So you can calculate ICQ is going to be 12 minus 5.3, that will be 6.7 divided by 500. So when you do this, that will be 12.6 milliampere, right? Like that. Check it. 12, find 5, 6.7. Yes. Oh, sorry, not 5. This is 7. Sorry. 0.7, because this is 0.7 here. Yeah, 0.7 plus 5, that is 5.7. So this will be 5.7. 12 minus 5.7 is 6.3. So yeah, when you divide this 6.3 divided by 500, that is 12.6 milliampere, right? 12.6 milliampere is ICQ, and yes, not ICQ, this is IEQ, because the current is going through this one, that will be the IB plus IC. So this is IEQ. You can convert this IEQ into ICQ. So ICQ is how much? Beta plus 1 divided by 100 divided by 101 times 12.6. So it's around 12.47. Only two options are there. Now we have to calculate VCQ. To do that, we will apply the KVL here. Alright, you can directly check it here. VCQ is the voltage across these two terminals. This emitter terminal is grounded, and this is 5.7. That will be 5.7 minus 0. That will answer is V. Yeah. Two transistors in the circuit given below are identical. If beta is 25, the current IC2, we have to calculate IC2. So basically, when you are seeing both the transistors are in forward active region, that this 25 microampere is the current, which is equals to this IC1 and the current of both the transistors, the IB1 and plus IB2, right? And both the transistors are identical, it means IB1 is equals to IB2. So we can say IC1 is equals to IC2. So we put these values and we will quote the formula that IC2 is beta times IB2 and IB1, and that will be beta upon beta plus 2 times 25. If you solve it, you will quote the value of this one, right? Like that. Yeah. That is the current mirror circuit with finite beta. You know that formula easily. In the shunt regulator shown in the figure below, the V2 is 8.2 and VB is equals to 0.7 volt. The regulated output voltage will be what? Okay, we have to calculate the output regulated voltage. So what we are seeing here, basically this is the output voltage at this terminal. That output voltage is VZ plus how much? The voltage across this terminal, that is VBE. So we can say the output voltage is VZ plus VBE. And yes, yeah, so VZ it is given to you, that is 8.2, right? 8.2 and VB is 0.7, so 8.9 is the output voltage. 8.9 is output voltage directly. Yes. Don't go for the second calculation, the answer is until here, right? That is not like that. 8.9 volt. The common emitter forward bias current, forward current gain of a transistor beta F is equals to 100. The transistor is operated in which region? So what you have to do, you have to assume this transistor in normal active region, and you can calculate the IB, IC and all values, right? And accordingly we can check it here. How much is the emitter voltage, how much is the base voltage, sorry, this is the collector, emitter, and this is collector voltage. And you can check that which junction is forward bias and reverse bias. Accordingly we give the answer. IB we calculate, and from this IB we calculate the VC value. If VC is greater than, right, if VC is greater than 0.2 volt, then we can say this is will be forward active mode. So here the active the transistor will be operated in forward active mode, right? Like that. Okay, next, the transistor parameter of Q1 and Q2 as shown in the figure, GM1 R pi, GM2 R pi. So what we do, we first draw the R pi equivalent of each transistor, this transistor and this transistor separately. You can see here, this is the first transistor of R pi equivalent, this is the second transistor R pi equivalent, right? So what from this circuit, what you are observing, that the output voltage we are calculating here at this terminal, this output voltage is equals to what, this V pi 2, or you can say R pi 2, right? Voltage across R pi 2. And yeah, and this voltage can be written as what, this output voltage can be written as what, this current GM1 and V pi 1 is going through this resistance, that is R pi 2, right? We can say like this. So this is your output voltage and input voltage, right? V pi 1 is equals to what, the input voltage, and we can replace that value, that GM1 into V input voltage, just V pi 1 is equals to V input, and we replace that value here. So V out over V input is going to be GM1 V pi 2 R pi 2, sorry, not V pi, R pi 2. So what we are observing here, that the transistor gain is follow GM, that will be GM1 R pi 2, GM1 R pi 2. So answer will be C from this circuit. Next, yeah, in the given circuit, the VTH is 0.7 volt and M1 transistor will be operated in which region? So first we calculate VSG plus VTH is 0.6 volt and VSD is VS minus VT, that is 0.7 volt. So VSD is greater than VSD sat, so it will be in saturation region because it is a PMOS, right, not NMOS. Next, the following circuit of the figure, in active region M1 is operated in which region? Again, that VGS we calculate, VG is equals to 1.5 volt, VS is equals to 0.5 volt, VGS is 1 volt, VDS we calculated, VD is 2 minus 0.5, 1.5 volt, and VGS minus VTH is 0.6, so VDS is greater than VGS minus VTH, so it will be in saturation region like that. Next question, the PMOS transistor is shown in the figure has parameter VTB, W, Kp dash like that, right? ID and VDS is given, you have to calculate ID and VD is given to you. VD is drain voltage, so you have this voltage VD, so we can easily calculate ID we can have, so we can easily calculate the RD. RD is what, VD minus 5 volt, VD minus 5 volt divided by ID. ID is how much, 0.5 is equals to what, yes, RD, and this is how much, 3 volt. So minus 3 plus 3, 2 divided by 0.5, that will be 4 kilo ohm. So what we are observing, that RD resistance is 4 kilo ohm. Now you can calculate the, yeah, from the Kp you can calculate this equation, ID is equals to Kp VGS minus VGS plus VTP whole square. So from this equation we calculate VSG, and from that we can calculate the VS is equals to VSG is equals to 2.49, and from that equation we can calculate the V5 minus VS upon RS. RS is going to be 5.02 kilo ohm. So answer is what, the D. Yeah. For the transistor shown below, the parameter are VTN is equals to Kn is equals to Q-point. We have to calculate, it's easy. Just use that VD is equals to VDS is equals to 10 minus 30K. This is not J, this is K. 30K times ID, and we put the values, and VGS is equals to what, that 10 minus 20K ID, and we assume that transistor in saturation. From this equation we plug in the value, ID is equals to Kn 1 VGS minus VTH whole square. We put that value, we make a quadratic equation in ID, and we got the ID value, 2 values for this ID. So if you assume that ID is equals to 1 ampere, VGS is going to be negative, it means that cannot be chosen, because we are assuming that the transistor is in saturation. So we choose the ID value, that will be 0.2 milliampere. So when 0.2 you choose, that will be satisfy VGS minus VTH VDS is going to be 4 volt, which is less than VGS minus VTH. It means our assumption is not correct, so we have to assume that transistor is in linear region. Now you can solve for the ID. You will got the two values of ID, and when you take ID is equals to 1.7 milliampere, you will got the IG value, which is not possible, minus 13.4. Now you choose ID 0.23, then you will got that this is 5.4 and VDS is less than 7.4. so it means what we are saying, that this transistor will be operated in which region? Linear region, and the current is 2.3 and the voltage is 3.1 volt, like that. Yeah, these are the questions from the operational amplifier. The circuit shown in the below, we have to calculate the output voltage. So basically, if 0.1 milliampere current is going from this one, this is a 5 volt voltage here, because these two terminals have the same voltage. Positive Vp is equals to Vn. So this is 5. You can apply the KVL. So 5 minus 0.1 times 10 is equals to output. So that is going to be 5 minus 1, 4 volt. Answer will be A. Next, we have to calculate the voltage gain of this one, right? So directly you can use that. This is Vp, V positive, you can apply the voltage division rule, that is 1 divided by 3 plus 1. So V plus is going to be V out by 4, and the same voltage will be here, right? Now you can apply the nodal at this one. So V minus Vi divided by 1 is equals to V minus V divided by 3 plus 2 is equals to 0. So you can use this equation and this equation. V plus is equals to V minus, so we will got that V out over Vi is equals to minus 8. Last question. Yeah, the circuit shown below, the value of V out is, we have to calculate the output voltage, right? You can see here. Okay, this figure is opposite, right? This is 6 volt, this is 3 kilo ohm, 5 volt, 3 volt. Come here. See, this is 0 volt here. So this means this will also 0 volt here, correct? And this is Vi, this is Vi. It means the output voltage of this one V01, that will be the same here, same here. Now what we can do, we can calculate the output voltage of this one, that will be here. So what we have to do, V2 plus V2 minus the current through the 6 ohm source. 1 second. Volt source, yes. So this will be 0 volt. It means the current is going from this terminal, right? That will be how much? 6 divided by 3, that is 2 milliampere. So that current will go through this resistance, because no current is going inside, that will current go through this one. So directly we can say the current is going up, no current going inside this one. So what we can say, the 0 minus 5 times 2 is equals to V out. So V out is equals to what? Minus 10 volt. Answer will be C here. So these are the some important questions that are related to analog electronics, and which are the most important for the ISRO exam. This time I bring the questions which are little bit you can say the where you need to be solve the questions, right? And it is most important for your ISRO preparation. So basically, if you want to join, if you want to prepare for your ISRO preparation, you can join YourPedia, because already the live classes is going on. We are discussing the signal and system, and parallelly we are going with the analog electronics. So hopefully these questions will help you in your preparation, and prepare well. Then best of luck from our side. Bye bye.